Advanced architectures and deployment with PyTorch. This laboratory, we called it classification and visual search. So in this laboratory, we, what we did is divided into major projects. First is the fashion item classification. Um, the goal is to build a custom mobile net like CNN that can classify clothing items. So the step one is data pipeline. We just prepare the data set. The typical operations is we resize the images to 64 by 64. We augmented it, data augmentation, convert to tensor, and normalize pixel values. Then um, train dataset and validation dataset are loaded. Next, the train loader and validation loader are created. So a neural network cannot train directly from images files, and the pipeline converts the image file and the tensor into the batch and to the GPU. So the inverted residual block, this is the first we did. So as a part of the activity, so the inverted residual block, this block comes from the ideas behind the MobileNet v2. So instead of having convolutional after convolution after convolution, we expand it first, and we use the depthwise convolution and project it. So what does expand means? And it increase the channels. Like for example, if we have the channels of 16 and it increased to 48 using the one by one convolution. And depthwise convolution is in the normal convolution, every filter sees all channels, but in depthwise convolution, one filter per channel, so much cheaper computationally. And next is projection. It reduces channels back from the 48 into 16 using another one by one convolution. So residual connection, if the strides is equivalent to 1 and the input channel is equivalent to output channels, so we could add them together. So output and input. This skip connection from residual training, or I mean residual learning, benefits is better gradient flow, easier training, deeper networks. Next is mobile net backbone. Here we use the mobile backbone. So the backbone extract images features. Let's say if we input the 3 by 64 by 64 and the output is 64 channels by 4 by 4, then backbone consists of stem, or the first convolutional layer, convolutional 2D, and transform it from the 3 channel to 16 channels. Next is feature blocks, stacks of inverted residual block. So the layers, the network gradually learns the edges, textures, patterns, and clothing features. Next is mobile net like classifier. This is a complete classifier. Mobile net like classifier structure is from the input image, backbone, to global average pooling, and then we flatten it and fed it to the linear layer, finally to have a class chorus logics. And the final layer predicts clothing categories, examples, shirt, dress, hat, shoes, and bag. Next is class imbalance. It computes the class weights. Why? Suppose dataset contains 1000 shirts and 100 hats only. And without weights, the model focuses mostly on shirts. Weighted loss tells the model mistakes on rare classes are more important. So next is training. We train using the Adam optimizer and step LR for the scheduler. When the accuracy or the training accuracy stop improving, so reduces the learning rate over time. So the training loop, each epochs for the forward pass, calculate the loss and the bug propagation and rate update. Next is evaluation. After training, we use the function display random predictions per class and shows predictions. This helps check correct predictions, incorrect predictions, classes the model struggles with. Next is visual search engine. This is one of the most interesting part. Instead of predicting this is hat, we want show me similar hats. This requires learning and an embedding space. Next is embedding space. Every image becomes a vector. Example, we have the hat and the other hat. They expected that they have similar vector values, but not exactly the same because they shared the same features like shapes, the edges of particular hat. So vectors for similar items should be close together for them. Next is triple dataset. So we use the triple dataset and produces the anchor, positive, and negative. So the anchor this is the original image. Like example, we have the image hat, and the positive on the other hand is the same class. So there's other class that belongs to that anchor. So that's example that another hat. And the negative is a different class. Example shoes. So a training sample looks like anchor, hat, positive, hat, and the negative is shoes. And Simon's encoder, the encoder converts images into embeddings. So the structure is we input the image, we do convolutional, and we do the feature vector. Example, the image and 128 dimensional vector. So Simon's network, the purpose is to learn similarity rather than classification. So the triplet-Lasky idea, distance between anchor and positive should be small, and the distance between anchor and negative should be large. So that's it. This is exactly our discussion last times regarding the relationships of the anchor and positive and negative in the vector space. So after training, embeddings organize themselves into regions like hat region, shoes region, dress region, and bag region. So images from the same category naturally clustered together. This is building the search catalog. And we compute the embeddings for all our catalog items. So every product receives a vector. Example, hat 1 vector, hat 2 vector, shoes, head vector, dress vector. And we did a query image search of the image of example. And the system converts query image into embedding, computes distance to all embeddings, sorts by nearest distance, and returns top matches. So the workflow from the query image, embedding, distance calculation, nearest neighbor, and top 10 similar items. So most concept that we should fully understand and retain in this laboratory is the custom convolutional network architectures, building networks from reusable blocks, and mobile net design using the depth-wise convolution, point-wise convolution, and residual connections for efficiency, and classification, predicting labels like hat, shirt, dress, and of course symmetric learning similarity instead of labels. So those embeddings, in the visual search, we use the embeddings and the nearest neighbor retrieval to find similar products. So the second half from the triple dataset, the Simon's networks, embeddings, and visual search. It's the same foundation we use in many real systems such as image search, recommendation system, face recognition, and product matching. It is also part of the most relevant to becoming successful in this field.